Okay, so let's start today's lecture. Okay, so now in the previous lecture, we have been talking about the Laplace transforms. Okay, so and how to, I mean, we've been talking about how Laplace transforms and the inverse Laplace transforms can be used. Okay, so can be used to solve differential equations. Okay, differential equations, and in particular, we've been focusing on this table of Laplace transforms. That's a very important table that you're going to see on your exams. Okay, so that's a very important table. And on this table, we've been kind of seeing that the first column are the functions in T. The second column are their fraction, are their Laplace transforms. Okay, and as I promised, for the rest of this chapter, indeed, we're just discussing line by line of this table of Laplace transforms. Okay, so you can see that from line 1, let's say, to line 10, right? So and I mean, even including line 12, 13, and 14 is something that we have been seeing already. So that we are going to kind of more or less look like the lower part of this table. Okay, so including the 16, 17, 18, like all these lines. So each of these lines is going to correspond to a very important theme of Laplace transforms that we will discuss throughout these lectures, upcoming lectures. Okay, so that's the major plan for the upcoming few lectures. Okay, so now starting from today's lecture, we're going to talk about step functions and the differential equations with discontinuous forcing. Okay, so they are basically corresponding to line. Okay, so they're basically corresponding to line line 11. Okay, so line 11, line 16. Okay, so and the 17. Okay, and 18. Okay, so etc. Okay, so we're going to introduce these few lines. Okay, so what is a differential equation with so let's say step function? Okay, so step functions and DiffQ. Okay, so DiffQ with discontinuous forcing. Okay, so step functions and DiffQ with discontinuous forcing. So how are this? What is DiffQ with a discontinuous forcing? Well, imagine that you are going to consider the vibration problem. Okay, so we've been talking a lot about the vibration problem. Okay, so before that, if you have the equation mu double dot plus gamma of u dot plus k of u is equal to the external forcing, right? So in this equation, m is the mass, right? So m is the mass. Gamma is what we call it the damping constant, right? So gamma is what we call it the damping constant. K is sometimes called Hooke's constant, right? So Hooke's constant, and the external forcing, this is the external forcing, right? So the Fe of T is sometimes called the external forcing, right? So this is like the second order differential equation that can model the vibrations. Okay, so it can model the vibrations. Okay, so and let me remind you that U is the relative position with respect to the equilibrium position. Okay, so it's the relative displacement with respect to the equilibrium position of the mass, and the downward direction is positive. Okay, so we're going to let the downward direction to be positive. Okay, so that's kind of the basic setup of this problem. Now, so far, when we talk about external forcing, the only model that we've been incorporating in this external forcing model is resonances, right? So resonances means that you would like to consider, let's say, is f of 0 cosinuses of omega of t with certain external forcing has a frequency omega, and if omega is equal to the intrinsic, right? So into the natural frequency, omega 0 square root of k over m, then you're going to have resonances, right? So this is just a review of what we have learned before regarding this vibration equation. Okay, so Now, what about the discontinuous forcing? Well, in let's say in a soccer game, right? So a discontinuous forcing appears, right? So for example, if you have a soccer ball player, you're kind of chasing this soccer ball, right? So it's moving, and when you hit, right? So when your foot hits the ball, you're going to give it a huge kick, and the ball is going to kind of move, right? So this is a typical example of a kick forcing, right? So or discontinuous forcing, namely, you're not kind of put your feet on this ball continuously, but you suddenly touch the ball and give it a huge momentum, and it's going to move, and then you're going to take away, right? So that's kind of about the discontinuous forcing, and the discontinuous forcings do appear in vibrations, right? So let's say you're considering a mechanical vibration. There is a certain mass is kind of oscillating, right? So it's kind of oscillating. Then what happened here is that maybe at some moment you're going to give the mass a huge kick, right? So you're going to kind of give the mass a huge kick, right? So as long as you give the mass a huge kick, it is going to start its motion, right? So it's going to start its motion being interrupted by the huge kick. So it is possible to happen that the right hand side of this vibration equation is a discontinuous function, right? So it's a discontinuous function. So that means we would like to kind of consider the discontinuous function more carefully. Okay, so for example, a very naive thinking is going to tell you that this discontinuous function can be modeled as follows. So let's say this is f of t, external forcing. This is time. So before time c, the external forcing is 0. At time c, the external forcing becomes f of 0 and on, right? So let's say f e of t is equal to, okay, so it is equal to the f. Okay, so let's say f if t is greater or equal to c, and it's 0 if t is less than c. So that's kind of a typical scenario where you're going to have a discontinuous force, right? So it's t, so that's something like this. Is that good for everybody? Okay, so that's the external forcing, right? So that's kind of the external forcing that you might see in a practical scenario. And such external forcing is called a step function. Okay, so it's called a step function. Remember, the step function is 0 before time c, and it becomes 1 after time c or equal to time c. So that means you have a kind of field dot. The dot is field at this point instead of here. Okay, so and here you're going to just have an empty dot. Is that good for everybody? Okay, so that's going to be the scenario for the step function. So now you can see that this step function can actually be decomposed into much simpler step functions. Okay, so the general step function has a building block. Okay, so which is a much simpler step function that we're going to call it the unit step function, or sometimes called the Heaviside function. Okay, so Heaviside is an electrical engineer who learned mathematics by himself, and because of his work in electrical engineering, he started to notice the importance of impulses that can jump. Okay, so such as electromagnetic impulses that can jump. So that's why he proposed this unit step function. So what is a unit step function? So let me take, okay, so let me take this definition. Okay, so this is the definition of the unit step function. Okay, so this is the definition of the unit step function. Okay, so let me put it here. Okay, so that's the definition of a unit step function. Okay, so okay, so that's the definition of a unit step function. Okay, so this unit step function is defined to be 0 if t less than c. So that what happened here is that if you draw a picture of this unit step function, then you're going to have the following picture. Okay, so then you're going to have the following picture that this function is equal to 0. So there is a c. Okay, so it is equal to 0 if t is less than c, and it is equal to 1 if t is greater or equal than c. Okay, so if t is greater or equal than c, the value is equal to 1. Okay, so that's a function of t. Okay, so that's a function of t. Okay, so that's kind of the same. So you're going to let some c to be positive, greater or equal than 0, and such that the uc, okay, so we denote this unit step function by uc of t. Okay, so with a subscript c. So the uc of t is equal to 0 if t is less than c, and it is equal to 1 if t is greater or equal than c. So that you're going to have this picture. Sometimes we also like to write this function as ut minus c. Okay, so if you write this function as ut minus c, it means what is your function ut? Well, you can see that the function ut is just 0 before time 0, and it becomes 1 after time 0. So this is a uc of t. And therefore, if you shift it, right? So that means if you consider ut minus c, then you're going to have the following picture, that this ut minus c is the function that before time c is 0, and starting from time c, it becomes 1, right? So it becomes 1 starting from time c. Is that good for everybody, right? So because you do ut minus c. Okay, the reason we introduce two such symbols is because they appear simultaneously in this class. Okay, so indeed, for now, on your exams, okay, so on your exams, you're going to see ut minus c. But if you, but because you are going to also work with the ODE exam problems from the student resources as a major practice, you're also going to see UC subscript, the CT appears very often in the previous exam papers. Is that good? Okay, so we're going to use both of them. Okay, so these are the so-called unit step functions. Okay, so these are the so-called unit step functions. Okay, so that's a unit step function. So you can see that in general, you can see that the external forcing taking this form is nothing but the magnitude of the forcing multiplied by ut minus c, right? So or uct, right? So uc of t, that's a unit step function. So this is kind of it can be reproduced from the unit step function by just multiplying by a magnification parameter f. Is that good for everybody? Okay, so that's about the unit step functions. Okay, so that's about the unit step functions. Okay, so now we're going to show you an example. Okay, so that tells you that how the unit step function can serve as the building blocks of very general step functions. Okay, so the unit step function can serve as the building block of very general step functions. Okay, so let us look at the following example. Okay, so this example says that can you express the function h of t of the u pi of t and minus u2 pi of t as a piecewise function. Okay, so that's a piecewise function. So you can see that you are going to have two unit step functions, but this is like a linear combination of these two unit step functions. We just combine them, right? So but this is going to create a certain kind of a piecewise function. Okay, so this is going to create a certain kind of piecewise function. So let's look at this h of t. So what does it do? Well, there is a u pi of t. So that means, let's say this is the function h of t. Okay, so and then you are going to have the function as a function of t, right? So what's going to happen is that before time pi, okay, so before time pi, u pi of t is going to be 0, right? So remember, uc of t is equal to 0 before time c. So before time pi, u pi of t is going to be 0, but the u2 pi of t is also going to be 0 because you have pi, you have 2 pi. Is that good, family? So that's going to be 0 minus 0. So it is just the value of the function is going to be equal to 0 before time pi. Okay, so before time pi. Then what's happening here is that starting from time pi, the u pi of t is equal to 1, right? So u pi of t is equal to 1, but u2 pi of t is still 0 because you're before 2 pi, right? So that's going to be the scenario. So that means, so basically you can see that this function is 0 minus 0 if t is less than pi, right? So it becomes 1 minus 0 if t is between pi and 2 pi. Right, so and it becomes 1 minus 1 if 2 pi is less or equal to t. Is that good, family? Right? So you have this scenario. So that means that you have a field dot here until you're going to reach 2 pi, right? So you're going to reach 2 pi. The value is going to, this is going to be empty dot. Because as long as t is equal to 2 pi, the u2 pi of t is equal to 1, and u pi of 2 pi is also equal to 1, so that the error is becoming 0 again. So you're going to have the function coming back to 0. So that's going to be your function h of t as a function of t. Is that good, everybody? Okay, so that's kind of you can see that simply by using 2 unit step functions, we're going to create such a function that is an impulse, right? So it's a 1 during the time period, but 0 elsewhere, right? So that's kind of showing you how unit step functions can be used as a building blocks of more simpler, building blocks of any kind of step function. So let's look at the inverse problem. Okay, so the inverse problem says, can you express the step function? Here is a step function, but I wanted you to kind of rewrite it as a linear combination of unit step functions. Okay, so let's look at this problem. Okay, so let's look at this problem. Okay, so that's going to, that being said, we are looking at expressing the following, this function into a unit step function. Okay, so we're going to kind of look at this function and we see if it can be written as unit step functions. Okay, so we can see that if it can be written as unit step functions. So what is this function? Well, this function, if you draw a picture of this function, it is simply something like this, right? So you have several breakpoints, right? So the breakpoints are equal to 4 as well as 7 and as well as 9, right? So and etc. Right? So let me make it like the gap a little bit larger in order to view the whole scenario. Okay, so you're going to have a 4, you have a 7 and 9. Is that good, family? Now the value of the function is equal to 2. Okay, so if you're less than 4, right? So that means you're going to have something like this. Now between 4 and 7, it is going to be equal to 5, right? So let's say this is equal to 5 between 4 and 7. Okay, so between 4 and 7, the value is equal to 5. And then starting from 7, the value becomes -1. Okay, so starting from 7, the value becomes -1. And starting from 9 on, the value becomes 1 again. So the value becomes 1 again. So this is actually a piecewise. Okay, so it's a typical piecewise function that you want to write it. Okay, so you want to write it as a linear combination of unit step functions. So what should we do? Well, first of all, you can see that if you don't have to, okay, so let me use, okay, so if you kind of ignore, okay, so if you ignore this several jumps of the function after time 4, you're going to just say, okay, so you're going to just say that let the function before the 4 extend, then this is nothing but 2. Right, so this first component is going to be just equal to 2. It's identically equal to 2 function if you kind of extend this 2. Okay, so so here is 1. Okay, so this one is 1, right? So if you kind of extend this 2 from 4 on, but starting from 4, the function 2 is being corrected. But how much correction do you have? Well, you jump from 2 to 5, the correction is 3. And how do you do that correction? Well, if you look at the unit step function, you're going to see that unit step function gives you the correction because the correction is 0 before time c, and it's 1 after time c. Is that good, family? So that means this correction being considered here is nothing but correction by 3. So that's like plus 3 times u4 of t, because you corrected each you correct this original function from 2 to 5, so you must correct by 3, and the correction happens at time 4, so that must be u4 of t. Is that good, family? Okay, so if you do not add future corrections, then the function is kind of just going to extend something like this. But you see that at point 7, you did another correction, and this correction is now from 5 to -1, so the correction is like -6, right? So the correction is kind of subtracting by 6. So you would like to correct by 6 of the function u7 of t, which means that starting from the point 7 and on, you're going to work with -1 because you already corrected by 6. Is that good for everybody? Okay. If you do this correction, then at point 9, you're going to do another correction, which is a correction from -1 to 1. The correction is by +2. So that means you're going to +2 multiplied by u of 9 of t. So that means at point 2, you correct it, I mean, at point 9, you correct it by a +2. You kind of jump back a little bit, and you get this. So this is like a nice linear combination of several of the unit step functions that can produce this piecewise step function. Is that good for everybody? And this is a very important idea. Okay, so this is a very important idea we introduced in this lecture, is that by doing these corrections, you can kind of move around your steps here and there and build a general step function that jumps back and forth. Is that good for everybody? Okay, this is going to be very important for your upcoming exams. Because in your upcoming exams, for some of those problems that, I mean, we are going to show you also about these problems, but for some of these problems, it is very important from the beginning that you are able to express the right-hand side of the equation by a linear combination of unit step function. That's why I'm emphasizing this. Okay, so this is going to be very important. Okay, so if you kind of a little bit lost here, you can kind of rewatch the video when you have time. I mean, how this function is being decomposed into several unit step functions. Okay, so that's going to be a very important and very nice example about this unit step functions as a linear combination. Okay, so the general step function as a linear combination of unit step functions. Okay. Now let us look at the theme of today's lecture. Okay, so what is the theme of today's lecture? Well, the theme of today's lecture is to consider the differential equation, vibration equation with the jumps, right? So that's kind of typically, you can see that, for example, we can consider a vibration equation. Okay, so gamma u dot plus k of u is equal to, let's say, external forcing multiplied by a unit step function, for example, right? So how are we going to solve? How are we going to solve such differential equation? Well, we would like to use Laplace transforms, right? So we would like to use Laplace transforms to solve such equation, which means that you're going to apply the Laplace transform on both sides of this equation. Okay, so k of u is equal to the Laplace transform of f0 uc of t, right? So you want to apply this Laplace transforms. And if you apply the Laplace transforms, because you have the fact that LU double dot, if you still remember, okay, so if you still remember, it is equal to s squared of the Laplace transform of u minus s of u of 0 minus the u prime of 0, right? So, and the Laplace transform of u dot is equal to s Laplace transform of u minus the u of 0, and therefore you can see that the left-hand side becomes mass multiplied by s squared Laplace transform of u minus s u of 0 minus u prime of 0, right? So initial conditions plus gamma of the Laplace transform of u dot is s Laplace transform of u minus u of 0, and plus k of the Laplace transform of u is equal to the f0 is a factor, so that's a constant Laplace transform of uc of t. So that's kind of Laplace transform. And if you have the initial conditions, u0 is equal to u0, u prime 0 is equal to v0, you're going to be able to express the left-hand side as linear combination. So ms squared plus gamma of s plus k multiplied by the Laplace transform of u, right? So minus ms of u0 minus m of v0 minus gamma of the u0 is equal to f0 Laplace transform of uc of t. And therefore, you are able to express the Laplace transform of u as an algebraic relation, and by inverse Laplace transforms, you intend to solve the u. So that's kind of our schematic plan of working with differential equations with discontinuous forcing. But then the problem here, okay, so then the problem here is that we would like to consider, to understand what is the Laplace transform of this kind of function that with jumps, right? So unit step function. what is the Laplace transforms of the unit step function? So this is kind of important, right? So that's kind of something that we want to understand. So want to understand, let's say, want to understand, right? So want to understand what is the Laplace transform of u of t minus c, or maybe we'll write it as uc of t. What is the Laplace transform of a unit step function? So how do we understand this? Well, we can calculate, right? So Laplace transform of uc of t. Sometimes we also write as a Laplace transform of t minus c. So this is a unit step function. And what's this unit step function talking about? Well, it is equal to 0 before c and equal to 1 after c. So that means you're going to have the 0 to infinity by Laplace transform e power s and t multiplied by u of t minus c dt. Is that good for everybody? Okay. But this function is going to be 0 before time c, and it's equal to 1 after time c. So that means from 0 to time c, you're going to kind of multiply since by 0, and starting from time c and on, you're going to multiply by 1 of dt. So that's kind of a very simple integral. Is that good for everybody? You're going to have nothing here, and then you're just integral from c to infinity e to the power s and t dt. And what's this integral? Well, this is going to be 1 over s, right? So e to the power minus s and t. So I'm going to use minus s. And the error happens at t equal to infinity and t equal to c. Is that good for everybody? Now, if t is equal to infinity, remember, usually we always assume that s is positive when we do the Laplace transforms, which means that if t is equal to infinity, the e power positive number multiplied by infinity is a limit which is equal to 0. So that in the end, you're going to just have 1 over s e to the power minus c multiplied by s, where the t is equal to c. Is that good for everybody? Okay, so that's going to be kind of a very important and very nice relation that simply tells us that Laplace transform of uc of t, right? So, or you're going to say the Laplace transform of ut minus c is equal to e to the power minus c of s divided by s. So where s is something positive. So that's going to be the Laplace transforms of the uc of t. Okay, so and this is indeed what we have been calculating. Okay, so what we have been calculating from this transformation. Okay, so and this is a very important line of this table of Laplace transforms, which is the line 17. Okay, so which is the line 17 on your Laplace transform table. If you look at that table, it simply tells you that ut minus a, where we're using u t minus c, but you can replace the c by the a, it doesn't quite matter. Ut minus a is e to the power minus a of s divided by s. So e to the power minus c of s divided by s. So that's kind of a very important line of this table of Laplace transforms. I would like everybody to understand. Is that good? Okay, so this is about the transformation of the function ut minus c. Okay, so that's a general unit step function. Okay, so general unit step function. Now, starting from here, we would like to also consider how does the Laplace transforms a general impulse function. Okay, so how does the Laplace transform is going to work through a general impulse function. Okay, so that's going to be kind of very interesting and going to be very, very important for our Laplace transforms that we're going to call it the shift table of Laplace transform. Now, once you understand the shift table of Laplace transform, the next exams, okay, so the next exams of your class will be very simple. But I can guarantee you that if you don't understand the shift table of Laplace transforms, you're going to have a very hard time for your upcoming exams. Okay, so this is a very important piece of table of Laplace transforms. Okay, so what is a shift table? Well, by shift table, it means that you can see that I'm here considering, okay, so here I'm considering, if you think of the Laplace transform of ut minus c, it means that before time c you have 0, and after time c you have 1. So this can be this can be regarded as a shift of the original jump function. So that means you're going to have 1 here, you're going to jump here. So that's kind of very simple function is being shifted to the right. by another by a magnitude c, you're going to have something like this. So that's going to be a shift, and you know that the Laplace transform of this shift is simply equal to e power minus cs divided by s. Is that good, family? But then we're going to have consider some very general shifts. So what is a very general shift? Well, the very general shift means that you're going to have a function of t, a very general function of t. If you shift this function, okay, so if you shift this function to the right by a magnitude c, then what you're going to happen? Well, then what's going to happen is that if you have shifted this function, so let me try to shift this function, okay, so let me try to shift this function, okay, so I'm going to do it in this way, okay, so I will kind of copy this function, just one moment. Okay, so just a moment. Okay, so I'm going to shift this function. Okay, so let's say to here. Okay, so I will shift this piece of function. Let's say I'm going to shift this piece of function to the right by some magnitude. Okay, so that's kind of going to be a shift. And the shift, let me assume, okay, so let me assume that the shift happens at point C, again at the point C. Okay, so that means before time C, the function is going to be 0, and starting from time C on, the shift is going to be f of t. So what is the resulting function? Well, the resulting function, I mean, if you just shift it, it can be written as ft minus c. So that means after time c, if you're kind of your magnitude, okay, so the farther away you're from c, the distance from c is actually the original distance from 0. Is that good, family? Okay, so and therefore ft minus c, this one can be viewed as a shift of the original function f of t. However, because everything is equal to 0 here, suppose f of t has some non-zero part like this, but then I'm going to shift it. I'm going to cut, okay, so I'm going to cut all these pieces of the function f of t before time c, before time 0. So that means here I'm going to have exactly 0 before the time c. So that's something like this. Is that good for everybody? Okay, so in the end, the function actually can be written as uc of t multiplied by ft minus c. Why is that the case? Because the uc of t is equal to 0 before time c, and it's identically equal to 1 after time c, which means that after time c, there's nothing but ft minus c. It's a shift of the function f. And therefore, before the time c, this uc of t is 0, no matter how is your f of t, is kind of being eliminated, and it just becomes 0. So that's going to be a shift, which is a general shift corresponding to the previous shift only to the step function. Is that good, family? Okay, so that means we would like to consider the Laplace transform of this shifted function f of t minus c. Is that good, family? Okay, so how do we understand the Laplace transform of this shifted function, right? So, and the idea is very simple. If you just perform this calculation, it's going to tell you that this Laplace transform of uc of t of ft minus c. Okay, so, and what is this Laplace transform? Well, by definition, it's going to be integral 0 to infinity s and t multiplied by uc of t multiplied by ft minus c dt. Is that good, family? Okay, so however, you can see that the uc of t is actually equal to 0 before time c. So that means it's just the c to infinity s and t multiplied by ft minus c multiplied by dt. Right? So that's you're going to just integrate from c to infinity. And if you integrate from c to infinity, you can simply say that this is e power s of t minus c, and then plus c, which is minus c times s, and then this is f of t minus c. I'm going to replace the t by t minus c. So in the end, you see that you can pull e power minus cs out, and then the integral after change of variable is just e power minus s multiplied by u f of u du, and this part is nothing but the Laplace transform of f. Is that good for everybody? Okay, so that means you're going to have e power minus c times s of the Laplace transform of f of t, original one. Is that good for everybody? Okay, so that's kind of very important. It means that we obtained such a very important formula that the Laplace transform of uc of t, f of t minus c, is going to be just equal to e power minus cs multiplied by the Laplace transform of f. Is that good for everybody? Okay, so this is the kind of what we call it the forward shift. Okay, so that's what we call it the forward shift. So what happened here is that you're going to shift the function f of t into the function uct multiplied by ft minus c. You shift the function to the right. So that's like an ordinary shift. Okay, so that's like an ordinary shift on the pre-image, and then it's going to result in a shift. But this shift, sometimes we call it the exponential shift. Okay, so sometimes we call it the exponential shift. By exponential shift, it means that you're going to just multiply by e power minus c multiplied by s. So that's an exponential factor shifted to the function. Is that good for everybody? Okay, so that's going to be an exponential shift. Okay, so that's going to be an exponential shift. Now, if you apply this function to this formula to f of t is only equal to 1. Okay, so if you apply this f of t equal to 1, you can see that uct multiplied by ft minus c is nothing but the function uct. Is that good for everybody? I'm just shifting the function 1. So that corresponds to the picture here. This is just the function y is being shifted into uc of t. Is that good for everybody? And we have this formula. Does this formula agree with our new observation of the shift table? And indeed it is so, because the Laplace transform of uct, according to this shift formula, it should be an exponential shift multiplied by the Laplace transform of 1. But we know that Laplace transform of 1 is equal to 1 over s, so that you're going to just end up with e power cs divided by s, which is exactly what we have been calculating. Is that good for everybody? Okay, so that means we are, in a certain sense, we have generalized this shift, the first shift formula into a very general shift formula, saying that if you shift the function to the right by c, there is the same thing as the exponential shift by minus c. So here one has to be careful that this shifts is with minus c here and minus c here. So the symbols, I mean the signs of the c's are going to be the same on both the left-hand side and the right-hand side. Is that good for everybody? Okay, so that's what we call it part of the shift table, which can be summarized as the following. If the Laplace transform, okay, so if the Laplace transform of a small f of t is equal to capital F of s, then if you shift the small f of t to the right by c, you're going to end up with uct multiplied by ft minus c. Then the Laplace transform is going to do an exponential shift where the minus c is going to be kept as minus c and capital F of s. Okay, so that means, so let me say, okay, so the shift table of Laplace transforms, which is going to be important. Okay, so shift table. Okay, so shift table of Laplace transform. Okay, so the shift table of Laplace transform basically says the following, that if the function f of t is under the Laplace transform is being carried to the function capital F of s, then if you shift the function to the right by c, you're going to end up with the function uct multiplied by ft minus c. Then under the Laplace transform, you're going to do an exponential shift e power cs multiplied by f of s. The important thing here is that this exponential shift has a factor minus c, which is the same thing as the minus c here. Is that good for everybody? Okay, so basically, shift table can be summarized as the following slogan. The slogan says that no matter what kind of shift, I mean, if you do an ordinary shift on no matter which side of this table, the other side is going to result in an exponential shift. Is that good for everybody? Okay, that being said, we actually have one more line of this shift table, which is going backwards. Okay, so that means I'm going to shift this capital F by C then by the inverse Laplace transforms, okay, so you're going to, as I said, you're always doing, no matter what side you're going to do a shift, on the other side, you must have an exponential shift. So that means you're going to have exponential ct multiplied by f of t. Okay, so you're going to have an exponential shift on the other side. So that means if you replace the f, you shift, you do not shift on this side, but you shift on this side, you shift f of s into fs minus c. You're going to result in exponential ct of f of t. Okay, so exponential ct of f of t. Very important thing here is that one has to kind of distinguish between a forward shift. So sometimes this is, sometimes we call it forward shift. Okay, so sometimes we call it the forward shift, and this one is sometimes called the backward shift. Okay, so sometimes this one is called the backward shift. So one has to kind of distinguish between the forward shift and backward shift. Okay, the forward shift is going to kind of no matter which shift you do, either forward or backward, you're always going to transform an ordinary shift into an exponential shift. That's common. Okay, so that's common. However, the difference here is that if you are doing a forward shift, okay, so if you are doing a forward shift, then the minus c is kept as minus c. But if you're doing a backward shift, then the minus c is becoming a positive c. So the forward shift and backward shift have different signs, right? So forward shift is going to preserve minus c as minus c, and backward shift is going to change minus c into plus c. Is that good for everybody? Okay. I will leave to you as an exercise to check that the backward shift is also working. Okay, so the same thing as the check that I did here. Okay, so that means I'll leave to you as an exercise to check that the backward shift also works. So e power ct of f of t is nothing but f of t minus c. Okay, so that's going to be the backward shift. By doing this, it simply means that you want to calculate e power ct multiplied by f of t, which is the integral from 0 to infinity of e power minus c times s, e power ct multiplied by ft dt, and blah, blah, blah. I leave to you as an exercise. Okay, so I won't be able to exactly do that, but I'll leave to you as a nice exercise. Okay, so you can just practice by yourself. But it is going to tell you the same thing. Okay, so that means that if you have an ordinary shift on the image, then you're going to have an exponential shift on the pre-image. But this exponential shift is going to have a magnitude c instead of minus c. Okay, so that's going to change signs. So that's the difference between the forward shift and the backward shift. So this is what we sometimes call the shift table of Laplace transform that you have to kind of memorize very carefully. Okay, there are two slogans. Okay, so there are two slogans that are very important for this shift table. One slogan is that no matter which side you do an ordinary shift, on the other side it must be an exponential shift. And on the other slogan is saying that the forward shift keeps the sign, and the backward shift kind of flips the sign. Is that good for everybody? Okay, so that's going to be the shift table of Laplace transform. Now, if you look at this table of Laplace transforms, the shift table are really given. Okay, so that means so line 11 is actually the backward shift. Okay, so that means you shifted the f into f, capital F into capital F s minus a. It results in an exponential shift on the pre-image by e power of at. And then line 16 is actually the forward shift. So you're going to shift the f of t into small f of t minus a multiplied by uat, or maybe we're going to say u of t minus a. You shift, all right, so you shift the original function to the right. Then it's going to result in exponential shift e power minus a times s of the capital F of s. Here, just they replaced our c by their a. Okay, so that means the line 11 and line 16 of this table are going to correspond to the shift table of Laplace transforms. Okay, and these shift table are going to be very important because we are going to be asking you to be able to transform back and forth using the shift table, which means that there are actually 4 different directions that you might be using about the shift table. Okay, so that's 4 different directions. So it can be forward or backward, or it can be forward or backward. So that means if you see a shift, ordinary shift on the pre-image side, you must know that there is an exponential shift on the image side. But sometimes we are going to compute inverse Laplace transforms. You see an exponential shift on the right-hand side, then it's going to be the ordinary shift on the left-hand side. But you might also see an ordinary shift on the right-hand side. It means it's an exponential shift on the left-hand side. So that really depends. If you want to eliminate an exponential, you have to use this table, but backwards. If you want to eliminate just a shift, you have to do this direction. It becomes the exponential shift. Okay, so that's really depend on calculation and your observation, and we're going to practice them throughout our lectures just to make sure that you understand the shift table appropriately. Okay, so that's going to be kind of very important for our future lectures. Okay, so in order to do this, okay, so let us just practice one exercise before we stop this section. Okay, so can you find the Laplace transform of this function? Small f of t is equal to sine t if you're between 0 and pi over 4, and sine t plus cosine t minus pi over 4 if you're larger than pi over 4. So that's going to be kind of a very important exercise. Okay, so that's kind of going to be a very important exercise that let's practice before we finish today's lecture. Okay, so let's practice this problem. So what does this problem say? Well, the problem is kind of giving you a step function. So that's why I say it is very important to be able to transform this function into, okay, so into a unit step functions, right? So you can see that it is nothing but saying that f of t is equal to sine t plus another function 0 if t is between 0 to pi over 4, and it is becoming cosinuses of t minus pi over 4 if the time is greater or equal than pi over 4. And so therefore, this one can actually be written as the sine t plus u of pi over 4 of t multiplied by cosinuses of t minus pi over 4. Do you agree with me? Right? So if you're not familiar with this old symbol, you can also say that sine t plus cosinuses of t minus pi over 4 multiplied by u multiplied by t minus pi over 4, where u is this unit step function that we have been considering. Is that good for everybody? Okay, so that means we're kind of doing what kind of shift? It's kind of an ordinary shift on the pre-image side. So that means if you want to calculate the Laplace transform of f, it is nothing but the Laplace transform of sine t plus the Laplace transform of this function cosinuses of t minus pi over 4 multiplied by u of t minus pi over 4. You're going to kind of shift everything to the right by pi over 4. Now, in order to calculate sine t, you're going to trace on the table, right? So what function you need for sine t? Well, you can set b equal to 1 is nothing but 1 over s squared plus 1. That's the Laplace transform of sine t. What about the Laplace transform of this object? Well, remember that here, this shift table is given in a very abstract way. So the shift table is either given like small f to capital F, or here is a small f to capital F. You have to choose. So here we can choose the small f and capital F in the following sense, that we understand that the Laplace transform of cosinuses of t, because here we're going to treat this small, this is going to be my f t minus pi over 4, which means that this cosinuses of t is going to be my f of t. That's going to transform into some capital F of s. But what is this capital F of s? You have to use the table again. So that's kind of typical. Sometimes you have to, your strategy is to combine several lines of this table and see how much you can explore. So that means you want to transform cosine t. That's going to be s over s squared plus 1. So that's going to be s over s squared plus 1. This is going to be your capital F of s that you'll be working with. Now you apply the shift table, which means that the cosine t is being shifted to the pi over 4. So you are going to have a forward shift. So this is a forward shift, right? So forward shift means that on the pre-image side, you're doing an ordinary shift. So that's going to be e power minus pi over 4. Remember, forward shift keeps the sign, multiplied by s, multiplied by capital F of s. Is that good for everybody? Okay, so that's going to be a forward shift. But if you don't remember the forward shift, it doesn't matter. You can just look at the table, right? So which line of the table we're working with? we're working with line 16 of the table, where we're going to set the small f to be signed so that the capital F is your transformation function. Is that good, family? And how is your choose A? You choose A to be equal to pi over 4. So that being said, you kind of result in the pi over 4 of the capital F of S, but the capital F of S is something that you already found from another line of this table is S over S squared plus 1. Is a good, family? And this is indeed the Laplace transform of the whole function. So you can see that sometimes you have to use the shift table together with some other lines of this table in order to make a full understanding of what happens in this scenario. Okay, so what happens in this scenario? Okay, so let us continue our discussion of the shift table in our subsequent lecture, next lecture. And that means this is the end of today's lecture, and I'll see you in the next lecture. Okay, see you in the next lecture.